Good evening. Today we are going to start with method of induction. It will be followed by binomial theorem because binomial theorem can be proved using method of induction only. See, in mathematics, many times some results are guessed by observing some pattern. And of course, mere guesswork is not sufficient. Then either we prove it or we disapprove it. For example, let us find sum of the first n odd numbers. The first odd number is 1. Second odd number is 3. So 1 plus 3, 4. Third odd number is 5. So 1 plus 3 plus 5 is nothing but 9. So can I say that this is 1 square, this is 2 square, this is 3 square? Let us find sum of the first 4 odd numbers. It is nothing but 4 square. So by observing this, can we say that sum of the first n odd numbers, clearly nth odd number is 2n minus 1. It is n square. Note that this is just guesswork. We have observed the pattern and we have guessed this. This is not the proof. But in mathematics, mere guesswork is not sufficient. We have to prove this. Otherwise, result may not be true, but we will say that no, this is absolutely correct result. I'll give an example. If I make a statement that n square plus n plus 41 is always prime, and I will say put n equal to 1. So 1 plus 1 plus 41, 43. Is 43 prime? Yes. Put n equal to 2. 2 square 4. 4 plus 2, 6 plus 41, 47. Is 47 a prime number? Yes. Put n equal to 3. 3 square 9 plus 3, 12 plus 41, 53. Is 53 prime? Yes. So if I conclude that n square plus n plus 41 always gives prime for natural value of n, then this is merely a guesswork. But for n equal to 40, you will notice that n square plus n plus 41 is what? 1681, which is not a prime number. In fact, if I'm not wrong, it is 41 square. So this guesswork is not correct. And therefore, in mathematics, the result which is guessed is denoted by P of n. Now, why to use n? Because here n stands for natural number. See, this is just a guessed result. Now, this may be true for some natural values of n, and may be false for remaining natural values of n. Now, we are interested in knowing whether this guessed result P of n is true for all natural numbers. That is, in proving it to be true for all small n belonging to capital N. Now, this method of proving such a result is provided by a principle known as principle of mathematical induction. Note that we are going to use this symbol. How will you read this? For all small n, this is inverted A. You have to read this as for every, for all. In 12th standard, we are going to discuss this quantifiers, existential and universal. This is universal for every, for all small n belonging to set of natural numbers. This should be true. So what is that principle of mathematical induction? Listen to me carefully. See, this is not at all difficult. After this, we will discuss 2 solved examples. So I'm sure after that we'll be able to solve remaining sums on your own. So what is that principle of mathematical induction? As I said, we begin with let P of n be a statement, that is result, associated with every natural number n. If number 1, P of 1 is true, that is the statement is true for n equal to 1, Second, P of k plus 1 is true. Let me explain first. If you have any difficulty, you can ask me later on. P of k plus 1 is true if P of k is true for some k, which is again a natural number, then P of n is true for all natural numbers n. I repeat this part. First, we verify that P of 1 is true. How to verify that? Put n equal to 1. If LHS is same as RHS, means P of 1 is true. Then we assume that the result is true for n equal to k, where k is a natural number. Assuming P of k to be true, we prove, we cannot assume everything. We can assume that P of k is true, but then we have to prove that P of k plus 1 is also true. That is, symbolically, P of k is true implies P of k plus 1 is true. See, this is interesting. So if P of k is true, we will prove that P of k plus 1 is definitely true. Now put k equal to 1. So this becomes, if P of 1 is true, P of 2 is definitely true. But in the first step only, we have verified that P of 1 is true. So P of 2 becomes true. Put k equal to 2. If P of 2 is true, P of 3 is definitely true. Now P of 2 is true. We have proved that. So P of 3 becomes true. Then P of 4 becomes true, and so on. So this is called as method of induction. So we say that by the principle of mathematical induction, the result is true for all small n belonging to capital N. Now let us discuss this using one particular example. We will discuss this example. Prove the following by method of induction for all small n belonging to capital N. 2 plus 4 plus 6 up to 2n is n into n plus 1. So this is how we have to present. Begin with, let Pn denote the statement 2 plus 4 plus 6 up to 2n equal to n into n plus 1 for all small n belonging to capital N. Instead of actually writing for all, you can use that symbol. Step 1. Verify P of 1 is true. So for n equal to 1, you may say put n equal to 1 here, or n equal to 1 means first term, which is 2. On right hand side, put n equal to 1. This also gives 2. So LHS equal to RHS. So we have verified that P of 1 is true. Now this is interesting. In the second step, we assume that for some k belonging to n, P of k is true. That is, we can replace every n by k. So 2 plus 4 plus 6 up to 2k is definitely k into k plus 1. See this. Now this is the most important step, step 3. Now we prove, we cannot assume everything. Now we prove that P of k plus 1 is also true. Means to prove, replace every k by k plus 1. Use common sense. These are in all how many terms? K terms. So we have to consider next term. So 2 plus 4 plus 6 up to 2k will be there, plus replace k by k plus 1. I hope you will put k plus 1 in bracket. Otherwise, you will say 2k plus 1. No, it is 2 into k plus 1. Replace k by k plus 1 on right hand side also. So again put k plus 1 in bracket. So k plus 1 into k plus 1 plus 1. That is k plus 2. I repeat this step. See, this is the most important step. We have to prove that P of k plus 1 is also true. That is to prove result obtained by replacing k by k plus 1 also holds good. Now, these are basically k terms. So we have to mention all those terms. Plus one more term. How to get that? Replace k by k plus 1. On the right hand side also, you have to replace k by k plus 1. So do that. Okay. So we have to prove this. Now LHS, 2 plus 4 plus 6 up to 2k plus 2k plus 1. Note that for these terms, see the cursor, for these many terms, I can directly write k into k plus 1. Why? From 1, we have assumed that this result holds good. So for this sum, I can directly write k into k plus 1. But this is to be added again, 2 into k plus 1. Take k plus 1 common. In another bracket, you get k plus 2. Yes, this is right hand side. This means if p of k is true, p of k plus 1 is definitely true. So in the last step, you have to say from all the above steps and by the principle of mathematical induction, the result p of n is true for all small n belonging to capital N. That is, for convenience, we have denoted this by Pn, but original result is this. So you have to mention that also. Is it correct? Okay. Rather, it is correct. Is it understood? I hope you understood that. In exam, you need not write this. Like this means if P of k is true, P of k plus 1 is true, that is P of k implies P of k plus 1, put k equal to 1. If P of 1 is true, P of 2 must be true. But P of 1 is verified to be true. So P of 2 is true and so on. You need not write this in exam. You can directly say from above steps, or at the most after this I will write P of k implies P of k plus 1. Therefore, from above steps and by the principle of mathematical induction, the result is true for all small n belonging to capital. Okay, one more sum. Now you just go through the solution and then I'll explain it. Second, 3 plus 7 plus 11 up to n terms is n into 2n plus 1. Actually, degree of difficulty is increased because here main job, not main, I should say, the first job is to find nth term. Now, 3, 7, 11 are in arithmetic progression with first term 3 and common difference 4. So what is the nth term for this? It is a plus n minus 1 into d, that is 4n minus 1. So we say let Pn denote the statement 3 plus 7 plus 11 up to 4n minus 1 equal to n into 2n plus 1. Okay, first step. For n equal to 1, LHS is 3. See, n is a natural number strictly. In induction, we deal with natural numbers only. So you may say put n equal to 1 here, or n equal to 1 means first term. So 3. What about RHS? 1 into 2 plus 1, again 3. This means result is true for n equal to 1, that is P of 1 is true. Then we assume, in the second step, we assume that result is true for n equal to k, where k is again a natural number. Means you can replace every n by k. So 3 plus 7 plus 11 up to 4k minus 1 must be k into 2k plus 1. So we have assumed that this is true. Let this be number 1. Now we have to prove that P of k plus 1 is true. That is to prove these terms as they are. One more term. How to get that? Replace k by k plus 1. So 4 into in bracket k plus 1. I hope you understand this. Here they have omitted that step. It is better if we write that. See these terms as they are. Now replace k by k plus 1. So 4 into in bracket k plus 1. So 4k plus 4 minus 1. That is why they have directly written 4k plus 3 equal to, on the right hand side also, k plus 1 into 2 into k plus 1 plus 1. That is 2k plus 2 plus 1. So 2k plus 3. When we will write this, we will mention that step also. Now prove this. Begin with LHS. See sum of these terms. See the cursor. Sum of these many terms from 1 k into 2k plus 1. But there is extra term 4k plus 3. Open all the brackets. You get this quadratic expression. What are the factors? K plus 1, 2k plus 3. RHS. This means P of k plus 1 is true. When we will actually write, we will say P of k is true implies P of k plus 1 is also true. So from above steps and by the principle of mathematical induction, the result P of n is true for all small n belonging to capital N. That is 3 plus 7 plus 11 up to n terms is n into 2n plus 1 for all small n belonging to capital N. Now third sum, exercise 4.1. Same question. Using method of induction, prove that 1 square plus 2 square up to n square, n into n plus 1 into 2n plus 1 upon 6 for all n belonging to capital N. You will remember we have done this in the topic sequence series. This is sum of the squares of first n natural numbers, right? Now, step 1, for n equal to 1, LHS is 1 square, that is 1. RHS again 1. So LHS equal to RHS, that is P of 1 is true. If this sum is asked for 4 marks, 1 mark will be for this particular step, right from let P and denote to this verification part. Step 2, let P of k be true for some k belonging to n. That is, replace every n by k. So 1 square plus 2 square plus 3 square up to k square, k into k plus 1 into 2k plus 1 upon 6. This is 1. So we have assumed that this is true. So in the step 3, we say we now prove that P of k plus 1 is true. That is to prove 1 square plus 2 square. See, these are k terms. You have to write all those terms. That is their sum. One extra term. How to get that? Replace k by k plus 1. I hope you won't say k square plus 1. No, square of k plus 1. Previously it was square of k. Now square of k plus 1. On the right hand side also you have to be careful. K plus 1, put that in bracket. K plus 1 plus 1 into 2 into in bracket k plus 1 plus 1. That is 2k plus 3. So we have to prove this. Okay. Begin with LHS. So it is 1 square plus 2 square plus 3 square. Now many students, they directly mention the last term. Don't do that. Why? See, for these underlined terms, their sum is already known to us. It is k into k plus 1 into 2k plus 1 upon 6 plus k plus 1 square as it is. Now the reason for this, from 1. In 1 we have assumed that this is nothing but k into k plus 1 into 2k plus 1 upon 6. Now simplify this by finding LCM. So LCM is 6. This is numerator. K plus 1 can be taken common to get this. Open all the brackets. You have to use common sense. See, in the required answer, we need k plus 1, k plus 2, 2k plus 3. We have already got k plus 1. So factors of this quadratic expression must be these two only. Of course, you have to verify. Otherwise, if you get 8 here and if you write k plus 2, 2k plus 3, you won't get marks for that, right? But why to waste time in that? So you will notice that this is nothing but right hand side. So P of k plus 1 is true. You need not write this in exam, but what does this mean? This means P of k is true implies P of k plus 1 is true. But you have to mention this step 4 from all the above steps, and by the principle of mathematical induction, P of n is true for all small n belonging to capital N. That is, for convenience, we have denoted this by Pn. That is 1 square plus 2 square plus 3 square up to n square is n into n plus 1 into 2n plus 1 upon 6 for all small n belonging to capital N. Okay, right now. Fifth one, 1 cube plus 3 cube plus 5 cube up to n terms is n square into 2n square minus 1. Here first we have to find nth term. Observe that bases 1, 3, 5 are in AP. So what is base in nth term? 2n minus 1. So statement P of n becomes 1 cube plus 3 cube plus 5 cube up to 2n minus 1 cube equal to n square into 2n square minus 1. Now first step, for n equal to 1, what is LHS? You may say we will put n equal to 1 here, or by n equal to 1 we mean first term 1 cube, that is 1. RHS 1 square into 2 into 1 square minus 1. So again 1, LHS equal to RHS, that is P of 1 is true. Step 2, let P of k be true for some k belonging to natural numbers, that is 1 cube plus 3 cube plus 5 cube up to 2k minus 1 cube is what? K square into 2k square minus 1. This is number 1. We are going to make use of this. This is sum. We are going to replace by this. Step 3, we now prove that P of k plus 1 is true. That is to prove, write these k terms plus one more term. Replace k by k plus 1. So previously it was cube of 2k minus 1. Now it is cube of what? In bracket 2 times k plus 1 minus 1. Open the bracket. 2k plus 2 minus 1. So 2k plus 1. See, I have written this 2k plus 1 cube. Now listen to me carefully. Right hand side will be square of k plus 1 into, in bracket, 2 into k plus 1 square minus 1. Remember, just expand everything. Factorization is difficult. Expansion is comparatively easy. I repeat this. Expand everything and tell me the polynomial. Open all the brackets. This will be what? K square plus 2k plus 1. Right hand side will be what? 2 into, in bracket, k square plus 2k plus 1 minus 1 and so on. Tell me the polynomial expression on right hand side. Use this method only, because obtaining answer in this form is not at all easy. Yes, so if you expand this, then we can say we have to prove 1 cube plus 3 cube plus 5 cube up to this equals 2k raised to 4 plus 8k cube plus 11k square plus 6k plus 1. Now begin with LHS. For underlying terms, I can say k square into 2k square minus 1, reason from 1 plus this. Now just expand. You will notice that you get the same, and you should. So this is right hand side. Means what? P of k plus 1 is true. That is P of k implies P of k plus 1. And after this we have to write, you may say step 4, from above steps and by the principle of mathematical induction, P of n is true. This is inverted A. How to read this? For all n belonging to capital N. But as I say, for convenience, we have written Pn. So you have to say that is 1 cube plus 3 cube plus 5 cube to n terms equals n square into 2n square minus 1. N belongs to capital. Right. Actually, sixth and seventh for homework, but I'll just show you the solution for sixth. But you should try first, and then if required, you have to go through the solution part. Okay. Now, seventh is again for homework. Just a minute, I'll give you one step, and then I'm sure you'll be able to solve that. Let me read sum number 7. Prove using induction 1 into 3 plus 3 into 5 plus 5 into 7 to n terms is n upon 3 into 4n square plus 6n minus 1. Right? So you will notice that each term is product of two terms rather. So here, nth term, I'm talking about 7 sum. Nth term comes out to be 2n minus 1 into 2n plus 1. Okay. Why? See, 1, 3, 5, 7 are in AP. First term 1, common difference 2. So it is 2n minus 1. Again, second numbers in the products 3, 5, 7. Again in AP, first term 3, common difference 2. So 3 plus 2n minus 1. So it is 2n plus 1. Okay. So I'll repeat this part. Seventh, let Pn denote the statement 1 into 3 plus 3 into 5 plus 5 into 7 up to what? 2n minus 1 into 2n plus 1, right hand side as it is. In this case also, it is better if you open the brackets. Instead of factorization, it is better if you expand, because expansion is easy. So this is about sum number 7. Let me explain solution for 8 sum, but please do write the solution after the lecture. Prove by induction 1 upon 1 into 3 plus 1 upon 3 into 5 plus 1 upon 5 into 7 up to 1 upon 2n minus 1 into 2n plus 1 is n upon 2n plus 1. I hope you won't say that is to prove take reciprocals. That is absurd. That is ridiculous. So we begin with let Pn denote the statement. Step 1. For n equal to 1, we get first term 1 upon 1 into 3, that is 1 upon 3. Or you may say we will put n equal to 1 here. Same thing. RHS 1 upon 2 plus 1, that is 1 upon 3. So LHS equal to RHS, that is P of 1 is true. Second step, we assume that for some k belonging to n, P of k is true. That is, replace every n by k. The result holds good. So this one. Say number 1. Now we prove that P of k plus 1 is true. That is to prove. See, why to say P of k? Because there are k terms. So what does P of k plus 1 mean? Addition of k plus 1 terms. So these terms will be there. Next term is obtained by replacing k by k plus 1. It is better if you write this step also. 2 into in bracket k plus 1 minus 1. So 2k plus 2 minus 1. That is why they have directly written 2k plus 1. Here 2 into k plus 1 plus 1. So 2k plus 2 plus 1. They have directly written 2k plus 3. It is better if you mention one more step. RHS k plus 1 upon 2 into in bracket k plus 1 plus 1. Then in the next step, simplify it to get 2k plus 3. Now LHS. So up to this sum we have assumed from 1, it is k upon 2k plus 1 plus this extra term. Now 1 upon 2k plus 1 can be taken common. To get this in bracket, how to add these? Find LCM, which is 2k plus 3. Numerator 2k square plus 3k plus 1. Now you know the answer, so why not to write these factors directly? But please check whether these are the same or not. So you will notice that 2k plus 1 gets cancelled. What remains is k plus 1 upon 2k plus 3. This is nothing but right hand side. So P of k plus 1 is true. So in the step 4 we have to say from all the above steps and by the principle of mathematical induction, P of n is true for all small n belonging to capital N. For convenience, we have denoted this by Pn. So you have to mention this also. Okay. So that's it for today.